So previously we discussed voltaic cells in which a spontaneous chemical reaction produces an electrical current. Electrolysis is the opposite. In this case, we're going to use an electrical current to drive some non-spontaneous reaction. One of the two common uses, which you see in the diagram over on the right, is the electrolytic decomposition or separation of a compound into its individual elements. So passing at least 2.36 volts of electricity through water will separate it into both hydrogen gas and oxygen gas in a 2-to-1 ratio. The 2.36 volts comes from the sum of the oxidation and the reduction half reactions. Right, so we have 1/2 reaction for water being 2H2O yields O2 plus 4H plus 4 electrons, and this has an E standard value of negative 1.53 volts. The other reaction for water is going to be 2 water molecules plus 2 electrons yields hydrogen and 2 hydroxide ions. This E standard value is minus 0.83 volts, which gives us a total of negative 2.36 volts. Right, so 2.36 volts is the minimum amount of electricity that we need to get this reaction to occur. So as long as we apply that amount, we're going to separate water into these two component elements. Now, the voltage will determine if the reaction occurs. What actually determines how quickly the reaction occurs is the amperage. The more amps we apply to this reaction, the faster the reaction happens. In addition, this particular reaction right here is usually catalyzed with a small amount of a strong acid because the H plus in solution will speed up the reaction. Now, one very noticeable change about electrolytic reactions like this is that these reactions generally take place inside of one container. So a voltaic cell, we separate the two half reactions from each other. In a electrolysis system, everything occurs in the same solution overall. So only distance will wind up separating it. There are no separate beakers, no salt bridge. The only reason why we have oxygen gas coming up through the anode and hydrogen up through the cathode is just because the gases will rise too quickly for them to really mix due to the physical separation of this what's called Hofmann apparatus. Right, so to get into a little bit more about how electrolytic separation works, we first have to note that the electrodes used in this type of reaction are inert. Right, so they're usually either graphite or platinum electrodes. Again, we kind of want inert things in our reactions because we want to minimize the possibility of side reactions that give us things we don't really care about. So to look at a separation, first thing we have to talk about is purity. If the substance we're electrolyzing is a pure molten salt, then what's going to happen is the cation is going to be reduced and the anion is going to be oxidized. So we'll take a look at an example electrolysis. We'll try to electrolyze Ki. Right, so Ki, when we melt it, is going to have K plus ions and I minus ions. Right, so when we look at K plus, what's the only thing that K plus can do? Right, it can't form another ion. The only thing that it's allowed to do is pick up an electron and become solid potassium. Same thing for iodide. All iodide can do, in this case we're going to need 2 of them, is donate a couple of electrons while becoming I2 solid. Right, so for a pure molten salt, all we do is just split up the 2 ions. The positive ion gains an electron, the negative ion will lose an electron, and they'll form whatever their general elements are. The other way that we can electrolyze a solution is if we had it in aqueous solution. For aqueous solution, we still have the 2 same reactions occurring with the cation and the anion, but now we have to add in 2 other reactions because as we saw in our previous slide, water can electrolyze as well, right? So water can produce hydrogen, it can also produce oxygen. So we have to account for those two reactions as well. And the way that we do this is actually very straightforward. Write out all the reactions, and then whichever reaction requires the least voltage to occur is the one that's going to happen. So here's an example of this in aqueous solution, still working with potassium iodide. All right, so let's put up all the common reactions. Right, so we have two possible reduction reactions. The reduction of potassium ions to potassium metal, same as we had on the molten salt. But now we add in the reduction of water into hydrogen. The other reactions that we have are the oxidation reactions, where iodide turns into iodine and water turns into oxygen. Now, just for sake of making my life a little bit easier, I'm actually going to take these because, again, these are reduction half reactions. When you're given these on the AP exam, you will usually be given the reduction reactions. If you want to make your life a bit easier, just turn them into the oxidations. All right, so here I'm going to have 2I minus yields I2 plus 2E minus, and E for this is negative 0.54. And then our water reaction down here, we have 2H2O forms O2 plus 4H plus 4E minus, and E standard for this reaction is minus 1.53 volts. Right, so now all we're going to do is we're going to figure out which of these numbers give us the most positive result. For our two reduction reactions, well, the one that gives us the most positive result here is water turning into hydrogen gas. Right, so that at 0.83. For our oxidation reactions, the one that gives us the most positive result is iodide turning into iodine. Right, so these are our two potential half reactions. Right, so the overall reaction for this process is that we're going to see 2H2O plus 2I minus form I2 plus H2 and 2 hydroxide ions. And one thing you'll see when I do this demonstration in class is that you'll see one electrolyte will start turning a dark brown as you start forming the iodine around it. The other electrode is not only going to bubble, which is the indicative of the hydrogen gas, it's also going to turn slightly pink because what's going to happen is I'm going to put in a phenolphthalein indicator, and that indicator solution will cause the hydroxide to show up as pink. Right, so these are our two half reactions, and E standard for this reaction overall will give us a value of minus 1.37 volts. Right, so we add 1.37 volts of current, we get these to split up into those components. Right, so that's electrolysis. Just keep in mind that when you have aqueous solution, you have to take into account all the possible reactions for everything in the solution. Another common use of electrolysis is electroplating. Electroplating is when you add a thin layer of one metal on top of another metal. So here in the diagram, the two electrodes that we want, one of them is the metal that we want to plate with, and the other is the object we're trying to plate. Right? They're put inside of a solution, a saturated solution of the plating metal. So in this case, we're putting it in a saturated silver nitrate solution. Right? So what they're trying to do here is just take a cheap steel spoon, coat it with a small layer of silver. When I told you guys that I spared every expense when it comes to this class, I meant it. I'm so cheap, I can't even be bothered to use pure silver fake silverware. I have to use silver plated fake silverware. Right now, when it comes to doing the math for this, the math couldn't be easier as long as you remember a couple of different conversion factors. The first one is that an amp is a coulomb per second, and the second is the Faraday constant, which is that 1 mole of electrons is equal to 96,500 coulombs approximately. The Faraday constant, by the way, is on your equations list, so you don't have to memorize the value. Now, while the couple of most common questions you'll see involve calculating time or calculating mass involving electroplating, realistically, you can be asked any question involving any type of electrolysis. And the reason why this is so easy is that it's literally just dimensional analysis, right? Just take the numbers you're given, convert units until you get into what you want. If you see a problem like this on the AP exam, you should be thanking the College Board for the free point. Just assuming you don't screw up the sig figs on it, right? So we'll do an example problem of electroplating, right? So here we have a copper in a +2 oxidation state, right? It's copper 2 chloride, and we want to be forming copper metal from this, and we want to figure out how long it will take at a current of 1.5 amps to plate out 3 grams. So if you want to try to solve this, pause the video, take a couple minutes to solve it, and then pick it up and we'll go over the solution and see how well you guys did. Okay, so for this, while you could start off using 1.5 amps as your initial number, I'm going to start off just using the 3 grams, right? So we have 3 grams of copper 2 plus. Grams, first place I want to take it's always to moles. So 1 mole of copper is 63.55 grams, right? Grams cancel. Now from from moles of copper, I want to find moles of electrons, right? The equation for this is that we have Cu2 plus 2 electrons forms copper solid, right? So every mole of copper 2 plus has 2 moles of electrons. Now that I'm in moles of electrons, I'm going to use the Faraday constant, right? So 96.5 coulombs is 1 mole of electrons. And then finally use the amperage, right? Remember 1.5 amps is 1.5 coulombs per second. So 1.5 coulombs to cancel that out there. 1 second. Plug that all in, and we wind up getting 6,070 seconds, or 1.69 hours to get into a kind of reasonable time frame. That's all electrolysis math is. Very, very straightforward. In the next video, we'll talk about how to relate electrochemistry to equilibrium and to thermodynamics.